Hey guys, this is Mr. Grun, and this is Chapter 7 Review. So what are the things you're going to need to know? When it comes to exponential growth and decay, you are going to have to graph. You're going to be able to identify graphs. You're going to have to identify whether or not something is growth or a decay function by a graph, by a word problem, by an equation. You're going to have to be able to write those equations and show your work, and there's going to be compound interest problems. When it comes to log functions, you are going to have to convert between the two forms, literally where you just rewrite it. You're also going to have to convert to be able to solve something. You're going to have to, and that falls under the evaluating log, so where your answer is actually a number, not a different form of the expression. You're going to have to be able to expand and condense log expressions, and then solving logs and exponentials with a one-to-one property. All right, so here we go. All right, something like this. Now, for this video, if you want to pause, try it on your own, and then unpause when you want to see it done. Okay, so we want to write a function that models this. So we've got a car that depreciates 15% a year, and we want to know what the value would be, a model based on for the value, if it was a $20,000 car to start with. So that is going to be 20,000 and 1 minus 0.15 to the t, or to the x. So that is our equation that we're going to use. Minus because it is depreciating, right? All right, graphing the function. Let's use a table to graph this. So if we plug in, now one way we can do this is if we just go to our graphing calculator and hit the y equals button. Let's get rid of some of this stuff, and we can do 20,000. 1 minus 0.15 is 0.85. You could do it as 1 minus 0.15 also, and we'll raise that to the x power. Now instead of looking at the graph, I'm going to look at the table, and so then I can really quickly figure out what my table of values is going to be, right? So at 0, we're at 20,000. After 1 year, we're at 17,000. That should be a comma. Then 14,450, and we'll say 12,283, we'll say, just because the 0.5 isn't going to fit into the table very well. Okay, then as far as graphing that goes, we just have to plot all of those points. So I'm going to use my calculator again, the table off of it. So at 0, we should have a height of 20,000, and then a height of 17,000. So we'll kind of have to guess where that is a little bit. Like if we broke it up into 5 pieces, 17 would be right about here. Then 14,450 is going to be pretty close to 15,000, a little below it. And then 12,282 is probably right about the halfway point here. So it's going to be fairly linear right now, but we know that what that's going to do, because we know the shape of an exponential function, it's going to kind of flatten out as it goes off to the left for an exponential decay function. All right, now going back to that, in what year will the car be worth $11,000? Now there's 2 ways we can do this. One is to use that table of values and just scroll around and see when it is actually worth 11,000. And it's somewhere in the 3rd year it's going to be worth 11,000. It starts the 3rd year worth 12,282. It starts the 4th year at 10,440, and so somewhere in the 3rd year. We could also solve that exactly using logarithms. So that would be 20,000. We'll use the 0.85 because it's easier. So when is that going to be equal to 11,000? So what I would do, I would divide both sides by 20,000. And so we would get 0.85 to the t is equal to 11 over 20, which is 0.55. And then now if I rewrite this as a log, it's going to be log base 0.85 of 0.55 is equal to t. And now I've got something I can plug into my calculator. So we'll press the math button, select our log base. Oops, we'll quit first. Clear all that out. All right, 0.85, 0.55, and look at that, 3.67. So somewhere in that third year. All right, next one, growth or decay, and then finish the following table and use that to graph. So looking at this, that 2 on the inside, that tells me that this is a growth function. So we know it's growth. We'll fill in the table. Now again, I could use my calculator and I could figure out, I could do the y equals, or I could just use the calculator and plug in 0, 1, and 2 and 3 in for x. I could also look at this and know that if I plug in a 0 for x, 2 to the 0 is equal to 1, so this is 5 times 1, which is 5. And this value right here, the 5, is our initial value. So when x is equal to 0, y is equal to 5. Then what's happening each time is it's doubling. It's times 2, and this is how many times you're timesing 2 is the exponent. So this one will be 10, then 20, and then 40. And so our graph is going to look something like this. Let's count by tens. 1, 2, 3, 4. And 1, 2, 3, 4, 5. So at 0, it's a height of 5. At 1 is a height of 10. And then it's doubling each time. And so it's going to start growing really quickly as you go to the right. And if we went to the negative side, it would be flattening out to 0 like that. All right, compound interest. Find the amount after 10 years, $6,300, compounded quarterly at a rate of 5.6%. So all of our important information, let's highlight that. Okay, so I know that this is compound interest, 1, because it says compound interest right here, but 2, because of the word compounded quarterly. So we're going to use our compound interest formula. Our initial value is 6,300, and then 1 plus our decimal percentage rate is 0.056, so don't forget to move the decimal place twice. Then our end value, if this is compounded quarterly, that is 4 times per year for 10 years. That's what our formula should look like. And so if we come to here, we can just plug all that in. 6,300, parenthesis 1 plus 0.056 divided by 4, and then raised to the 4 times 10, which is 40. And depending on your calculator, you may have to use parentheses if you're going to do 4 times 10. Oops. In this case, I could just do 4 times 10 and it's in the superscript, or you could just in your head do 4 times 10 is 40. And we get that, so there's our answer. 10,986 and 48 cents. All right, our log functions, rewriting in exponent form. So anytime we're doing these, it's just the second 2 numbers that switch places, right? So instead of log base 2 of 32 equals 5, this is going to be 2 to the 5th is equal to 32. And in the other one, we're going to change it to log form. So it will be log base x, the first term, and then switch the 5 and the 3 around. Log base 5 of 3, log base 5x of 5 is equal to 3. All right, log functions, evaluating this and rounding to the nearest tenth. This is just calculator stuff. So hit the math button, log base 3 and 210, and that gives you your answer. it says to the nearest tenth, so let's go 1 decimal place, 4.9. The other way you could do this, if your calculator didn't have the log base function, is you could do log of 210 with an end parenthesis and divide that by log of the base, which is 3. And you get the same thing. All right, the next one, we could use the calculator for this one, but we really don't need to. If we think about it this way, right, we're really solving it for x. Then if we switch it to exponent form, it's 3 to the x equals 27, which then it's asking what power gets you from 3 to 27. Well, 3 times 3 times 3 is equal to 27, so that means that x is equal to 3. All right, condensing and expanding using log properties. So condensing this one, we're condensing it into one logarithm. So it's going to be log base 3, and everything else is going to be like right next to it here, right? The 5, the x, and the 2. Because there is a subtraction, this is going to involve a fraction. It's not just a big product. And anything that was a positive log is going to be on top. Anything with a minus log will be on the bottom. So 5x over 2. Then our next one here, this one, we're just plugging it or unplugging it, right? So the 3 is going to move over, and this will be log of x cubed. All right, now expanding it, we're going to switch this into 3 logarithms, one for the a, one for the b, and one for the 5. So sometimes what is good is just to write out all the different things. So log base 3 of a, log base 3 of b, and log base 3 of 5. And then we just have to think about what the sign is. Anything on the top is going to be a positive log, bottom's going to be a negative log. So the log a is positive, the log b is also positive, so we'll put a plus in the middle. But then the log 5 is going to be negative because it came from the bottom, so minus log 5. All right, and the last one, now we're just plugging this, right? So this is going to be 5 log base 2 of b. All right, solving. Using our 1-to-1 property, log base 2 of 2x minus 3 and x plus 4, we can really just disregard the log base 2 for both of them and just solve the algebra. So 2x minus 3 is x plus 4. And now we can move the x over to this side, and we get x minus 3 is equal to 4. And we can add the 3 to both sides to get x is equal to 7. And then the last one, pretty much the same thing. We just need the exponents to match. The 7's already match, so 3x plus 4 equals 6x minus 2. Now I'm going to move the 3's over, the 3x's over to the right side. It technically doesn't matter, but if you can keep your variable positive, that usually works out a little bit better. Add 2 to both sides, and we get 6 equals 3x. We can divide both sides by 3 and get that x is equal to 2.